Hello everyone, welcome to lecture 25 of the online course Modern Display Technologies Flat Panel Display. Today we will be introducing the reflective LCDs. So, here is the lecture outline. We will first discuss why reflective and transreflective LCDs, and then we will go into the motivation and trade-off and compare the transmissive reflective ones. We will then go into the details of the reflective LCD device architecture, discuss about the direct view versus projection kind of application, and then we will look into three popular reflective LCD or RLCD operating modes, which is vertical alignment VSL, then film compensated homogeneous cell design, and the mixed mode twisted nematic, that is MTN cell and its reflectance equation. Finally, we will be comparing the RLCD operating modes and apply the design rules. So, that will, to conclude, we will summarize and also lay down the bridge for the next lecture, which will be on the transreflectors. So, let us discuss why reflective and transreflective LCDs. So, in this lecture, moving from the transmissive LCDs that was studied earlier to these reflective and transreflective LCDs, okay, this could solve the power consumption and the outdoor readability problems of the backlight driven displays. So, if you remember that the transmissive LCDs have limitations because they need a backlight on at all times. So, that leads to high power drain, and bright ambient light such as sunlight basically washes out the image by surface reflection. On the other hand, the reflective LCDs or RLCDs, they have no backlight. So, it basically reuses ambient light to form the image. So, in a form, it is a very low power, lightweight and excellent outdoor readability can be obtained from this kind of displays. However, they also have weaknesses. So, these are unusable under dim or dark surrounding conditions when there is no ambient light to reflect. So, that is where transreflective LCDs come into picture that can combine both reflective mode under the bright ambient light and can also offer you the transmissive, that is the T mode, with backlighting in the dark condition. So, this is basically bringing the both together at medium brightness level. Okay. So, this is how it works, and the primary application space is the cell phones, digital cameras, PDAs, GPS unit, okay, and any other handheld display that you use for both indoor and outdoor applications. So, it is very easy to understand that the transmissive displays depend on the light source that is there for backlighting. Okay. So, in short, you can say that this works very well in dark environment, but it wastes power and it loses contrast in bright ambient light. So, it is not good for outdoor usage. On the other hand, the reflective ones, they use the light source which is available in nature. So, you can say the light source is basically the ambient light itself. So, near zero backlighting power basically draws very little power. Yeah. So, the power requirement for reflective is almost 0, but it fails in dark. So, the transreflective ones, they basically work for both, where each pixel area is basically shared or time shared between the reflective mode and the transmissive mode operation using both light sources as and when needed. So, what are the technical challenges? The transreflector design has to be done properly, so that each pixel can have both modes. And then the unequal optical efficiency between the reflection and the transmission mode may also cause some problem. Moreover, you can also see color mismatch and difference response time in the two modes. Okay. So, the module roadmap should be something like that. Here we are seeing the reflective LCD basics, from which we will be trying to develop the transreflector. Then we will go for the classification of the transreflective LCDs, and we will discuss about the cell gap design and the performance. Now, couple of important points to remember here is that the transmissive LCDs modulate backlight only. Okay. So, the whole optical stack, that is the polarizer, liquid crystal, and then the polarizer, only has to work for the light traveling one way. Okay. While you see the reflective mode LCDs, they basically modulate the ambient light, which basically makes a round trip. So, it gets in through the front, okay, and it bounces off the rear mirror, and then it comes out back from the front again. So, in that case, the reflective mode, the light basically makes a double pass. So, that is why the reflective cell gaps end up nearly typically half of that of the transmissive one, so that you can match those. Okay. So, the transreflective LCDs must satisfy both single pass, that is for the transmission mode, and double pass for the reflective mode optics within the same pixel, which is the root of almost every design difficulty that you will see in this particular discussion. And a cell gap or retarder that is correct for one pass wavelength is generally will be wrong for the second one. Okay. So, a dual cell gap or a patterned retarder or some kind of mixed liquid crystal modes are basically used. So, now let us look into the reflective LCD device structure. So, the figure basically shows the device structure of direct view reflective LCDs. Okay. So, the front stack shows single linear polarizer, and then you have a broadband quarter wave plate, okay, together with an equivalent crossed polarizer. Okay. And these two together, this single linear polarizer plus a broadband quarter wave film, they basically act together as an equivalent crossed polarizer, because most of the reflective LCD modes, they need this cross polarizer condition. And then you see at the bottom there is this is a color filter, this is the liquid crystal molecules here, this is the bumpy reflector at the bottom. So, this is the single most critical layer, because it reflects the light back to the viewer and diffuses it. So, it basically widens the viewing angle, and it steers the light away from the specular or mirror like glare. Okay. And then beneath this bumpy reflector, the TFTs, thin film transistors, are basically hidden. So, this basically lets the reflective LCDs to reach a very large aperture ratio of about 90%, because you do not need to waste space for this TFT separately, it can be hidden beneath. Okay. So, in that is how the reflector itself doubles the usable pixel area. And finally, you have a bit of this light blocking area. This is a black matrix like absorbing layer that basically absorbs the light scattered sideways from the neighboring pixels. So, that basically prevents the color and the contrast crosstalk. So, now let us compare the direct view versus projection reflective LCDs. Direct view reflective LCDs, they use ambient light directly for reading the displayed image, and the typical applications are handheld games, signage, or some cell phones. On the other hand, if you see the projection RLCDs, they basically use arc lamp or bright LEDs to project the image onto a large external screen, and there the liquid crystalline silicon or LCOS technology used in the rear projection TVs becomes a classic example of this kind of projection RLCDs. So, what you see that although the panel resolution and the surrounding optical systems differ substantially, both categories basically rely on the same underlying liquid crystal operating modes, which are covered in this lecture, that is the VA, homogeneous or the MTN modes. Okay. Now, why this particular course focuses on direct view? Because when you go for the transreflective devices, something like in phones, cameras and GPS, okay, they are basically all direct view products, okay, and the projection specific optics are mentioned only where they could affect a design choice, okay, like higher contrast ratio projection systems demand. With that, we can move on to the three popular reflective LCD operating modes. The first one is the vertical alignment or VA cell. So, it is already covered in the previous lectures for the wideband or wide view LCDs. So, what happens for reflective LCDs, we have seen that the cell gap is simply halved to compensate for the double pass, and the voltage reflectance behavior basically mirrors the transmissive VA curves. Okay. Then you have the second one is the film compensated homogeneous cell, that basically uses the liquid crystal layers phase retardation directly with an added compensation film to create a common dark state across red, green and blue. Now, the third one will be the mixed mode twisted nematic cell. Okay. So, mixed mode because here the light's polarization state is changed partly by the liquid crystal's twisting structure, okay, that is like the polarization rotation as in a twisted nematic cell, and partly by pure birefringent phase retardation, which is in contrast to the pure twisted nematic cell, which relies almost entirely on the polarization rotation. So, this mixed mode twisted nematic cell basically combines the polarization rotation as I mentioned with the birefringence. The liquid crystal twist angle can range anywhere from 0 to 90 degree. Okay. So, you can see that the VA and the homogeneous cells rely purely on the phase retardation effect, and the MTN cells rely on a mixture of phase retardation or polarization rotation and birefringence effect. Okay. So, the choice of mode can be designed like that. So, you can favor the film compensated VA modes, okay, for high end transreflective LCDs that can give you the best contrast plus the widest view, and you can choose homogeneous and MTN options trade off the simplicity, cost and the viewing angle. So, this homogeneous and the MTN basically gives you that compromise between the simplicity, cost and the viewing angle. Now, here we will focus on the single most important number for a film compensated homogeneous RLCD. So, we will talk about the minimum optical retardation d delta n that you see, okay, for the liquid crystal layer, and it will also show that it works for this particular standard design wavelength of 550 nanometer, which is the peak of the human photopeak sensitivity, okay, that belongs to the green wavelength region. So, what you see here is that the film compensated homogeneous cell, this is not viable for transmissive displays because a homogeneous cell has a narrow viewing angle and no common dark state for R, G and B in the transmissive mode. However, it works very well in the reflective mode, because the mirror image effect of the rear reflector basically makes a single domain homogeneous cell behave optically like a two domain cell. So, that basically widens the usable viewing angle. And the third thing that I was discussing about is the minimum retardation requirement. So, under the crossed polarizer conditions, a liquid crystal's birefringent layer must act as a quarter wave plate to rotate linearly polarized light into a circularly polarized light, or vice versa on the return pass, and therefore, that could produce a clean dark bright switching contrast, right. So, or you can say bright dark switching contrast. So, what you understand that d delta n must be at least equal to lambda by 4. So, if you consider this quarter wave design, okay, you will see that the cell gap, that is d, and the birefringence, that is delta n, that can be chosen independently, right, but their product should be lambda by 4. Okay. So, thinner gap will give you faster response, and however, lower n will give you easier, or you can say higher yield manufacturing. So, that is where you can choose this independently. So, if you consider the quarter wave design condition, d delta n is lambda by 4, and we are considering lambda equals 550, that is the peak of the human photo peak sensitivity. So, d delta n comes out to be 137.5 nanometer. Now, here we basically show reflectance and the need for a compensation film. So, look at the bright state in figure 2a. Okay. So, this is showing you the voltage dependent reflectance of a homogeneous cell with d delta n equals 137.5 nanometer, we just calculated in the previous slide, and this is the uncompensated one. Okay. So, what you see here is that the RGB reflectance intensity vary by less than 10% at V equals 0. Okay. So, they are within this range, and this is acceptably white bright state without any compensation film. Now, when you look into the other state, the dark state, at high voltage the reflectance only decreases monotonically, and you can see that the R, G and B, they are never reaching a common minimum. So, a true black or a true dark state is not achievable with this liquid crystal alone. Okay. So, what you do? You basically use the fix is to use a uniaxial A film. Okay. So, adding a compensation film with d delta n of that film to be equal to minus 48 nanometer. So, that basically makes your d delta n to be around 137 nanometer. So, that could cancel out the residual boundary layer phase, and it restores a common RGB dark state that you can see here. Okay. So, what is this basically showing? This is the film compensated homogeneous cell, where the liquid crystals d delta n is now 184 nanometer, with the A films d delta n to be minus 48 nanometer. Okay. You can also use a positive A film as an alternative, that also works, provided its optic axis is basically perpendicular to the liquid crystal rubbing direction. So, what are the example materials that can be used? Okay. So, here you can see that Mark MLC 6297000, this particular liquid crystal has delta n ranging from 0.125 to 0.129 across RGB, Pre-tilt angle alpha equals 2 degrees and the polarizer to the rubbing angle is beta, that is equal to 45 degree, and the elastic constants K11, K22 and K33 are mentioned here, okay, and delta epsilon is 6.9. Okay. So, what could be an alternating design point is that right now a delta d delta n equals lambda by 2 design has also been demonstrated with the benefit of weaker color dispersion than lambda by 4 design. The dark state width, how it changes with the voltage swing. So, if you consider a smaller magnitude composition film d delta n, that will give you a broader temperature tolerant dark state. However, it requires a larger voltage swing to reach it. So, why does this trade off matter? Because the driver IC design should also budget for this kind of required voltage swing. So, when your display reliability engineering is caring about how much the dark state basically drifts with the panel's temperature change, right. So, this swing is very important to be taken into consideration in the design phase itself. So, in this particular slide we will talk about the mixed mode twisted pneumatic cells. So, this basically provides the formula, master formula that predicts how much light a reflective MTN cell sends back to the viewer as a function of the applied voltage, cell parameters and viewing geometry. So, it is derived from the extended Jones matrix method. So, it basically describes the normalized reflectance R perpendicular of the null voltage, that is voltage of condition MTN cell. So, you can see the formula here, it is R perpendicular will be gamma square sin x by x whole square sin 2 beta cos x minus 5 by x into cos 2 beta sin x whole square. So, gamma is basically 2 pi d delta n by lambda, x is basically square root of phi square plus gamma by 2 whole square, d is the cell gap, phi is the twist angle and beta is basically the angle between the polarizer axis and the front liquid crystal director. So, what is the twist angle range? Unlike the fixed 90 degree twisted pneumatic cell, this mixed mode twisted pneumatic can twist anywhere, they can be tuned between 45 degree to 90 degree to trade off the contrast ratio against optical efficiency. So, in transreflective LCDs typically the 75 degree and 90 degree MTN variants are commonly used. So, we will basically compare those in the later slides. Also this MTN mixed mode twisted pneumatic cells, they show the voltage reflectance curve show relatively insensitive to the wavelength. So, which is why the simulations basically average the reflectance over each RGB color band. So, the R you can average over the 620 to 680 nanometer, G can be averaged over 520 to 560 and B can be from 420 to 480 nanometer, right. Now, if you carefully look into the equation, this gamma is the retardation phase that basically grows linearly with the cell gap and the birefringence delta n, and the exact same physical quantity that is controlled in the homogeneous cell design rule. So, here it is basically the only thing is that it is just expressed as a phase angle rather than a length. X on the other hand is basically showing you the effective rotation that basically that blends with the geometric twist phi with half the retardation phase, okay, into one parameter. So, you can see when phi is 0, this basically reduces to pure phase retardation case, that is of a homogeneous cell, confirming that these two modes are related limits of the same physics. Beta is the polarizer director angle. So, a pure geometry or manufacturing choice. So, it is actually independent of the liquid crystal material, and it can be freely tuned to help shape the VR curve without changing any material. Now, squaring the whole expression that you see here, that basically gives you the reflectance, which is an intensity or the power quantity, and it is proportional to the square of the reflected electric field amplitude, and that follows the standard optics convention. And the voltage dependence here basically comes when you apply a voltage that basically reorients the bulk liquid crystal detector. So, that drives the effective d delta n, and hence your retardation phase and effective rotation, okay, they all goes towards 0, okay, because that is where the alignment with the field happens. And this is the physical mechanism that produces the voltage dependent reflectance or the VR curve, right, that we have been discussing. So, here we are basically comparing that 75 degree versus 90 degree mixed mode twisted dematic cells performance. So, the first graph shows 90 degree MTN, the second one shows 75 degree MTN, okay, and these are simulated with Mark MLC 6694000 liquid crystal, where delta n is considered to be 0.857 at 540 nanometer, right. So, from that, the first thing that is considered, d delta n is around 240 nanometer, beta is taken to be 20 degree. So, you can see that for this particular case you get excellent dark state because of the cell phase compensation, okay, like the transmissive twisted nematic cell. But only thing is the limited peak reflectance only at around say 88%, that is the maximum that you are getting, right. However, when you move to the 75 degree MTN cell, their d delta n is around 250 nanometer and beta is 15 degree. So, what you see, you are actually getting almost 100% peak reflectance. However, if you see the dark state, there is a leaky, slightly leaky dark state. However, you get a contrast ratio of around 100:1 at 5 volt RMS. Okay. Now, the question is why the dark state leaks at this particular case in this particular 75 degree cell. So, the reason is its two boundary layers do not perfectly self compensate each other, unlike that happens in the case of 90 degree symmetric case, right. So, with that we move on to how to choose an MTN twist angle for a particular application. So, if you are talking about the direct view displays like phones, cameras, GPS, 75 degree MTN is the right choice. The surface reflection of the outer protective film already limits the contrast to roughly 100:1. So, 75 degree cells higher brightness is essentially a free extra performance, and the projection displays which requires the liquid crystal on silicon, rear projection TVs, that is where you get these projection displays. They need contrast ratio beyond 1000:1. So, that is well past what the surface reflection alone could limit. So, only 90 degree MTN or a vertical alignment cell can deliver that kind of contrast ceiling. So, the general design principle is that you need to match the liquid crystal mode's contrast ceiling to what the rest of the optical system can actually resolve. Chasing the contrast the system cannot use will just sacrifice the brightness for no visible benefit. Okay. So, if you see that this is where exactly the direct view versus projection distinction was discussed on slide 6, Here it is now made quantitative. So, the final comparison for the different reflective modes: vertical alignment gives pure phase retardation, the cell gap simply halved from the transmissive design. They can offer best in class contrast and viewing angle, which is favored for high end transreflective LCDs. We have seen the film compensated homogeneous cells, where you get pure phase retardation, and there is a need for compensation film to give a common RGB dark state. However, it is simple, low cost, however gives moderate performance. When you talk about mixed mode twisted nematics, you can twist between 48 degree to 90 degree. So, mixed polarization, rotation and phase retardation effect come into picture. Twist angle is a tunable trade off between the dark state quality, because you get very good dark state at 90 degree, however, you get much better peak brightness at 75 degree, right. So, here you see that every mode's performance ultimately traces back to the controlling the same underlying quantity, which is basically the liquid crystal layers optical retardation, that is d delta n for a specific geometry. So, to summarize, the reflective LCDs use only ambient light and which are reflected of a bumpy rear reflector, vertical alignment, film compensated, homogeneous and multi-mode twisted nematic. These are the three common liquid crystal operating modes. Homogeneous cell design rule is that d delta n will be lambda by 4, which is calculated to be 137.5 nanometer at 550 nanometer wavelength. Okay, that is the peak of the human photo peak sensitivity. A phase composition film can be is required to give you the common RGB dark state, and the MTN cells, they are basically governed by this Jones matrix reflectance formula, and the twist angle basically trades off the dark state quality at 90 degree, okay, against the peak brightness which is achievable at 75 degree. So, this is basically matched to the direct view versus the projection kind of applications. So, the common thread, as I mentioned, that every reflective LCD mode's performance basically comes down to controlling their liquid crystal layers optical retardation d delta n for a specific double pass geometry. So, in the next lecture we will look into the transreflector, that is the added component that lets a backlight coexist with this reflective structure. So, it will basically allow you to have the reflection and the transmission mode both in a given pixel, okay, and 4 transreflector families will be now covered in details in the next lecture. With that, we conclude here. Thank you for your attention. If you got any query, you can drop an email to this email address mentioning the course name and the lecture number on the subject line. Thank you.